Hello, everyone. Welcome to the first talk of this afternoon. The talk will be given by Professor Mark Shusterman. He's from Wisma Institute. His title is Twin Prime Polynomials over Finite Field. So let's welcome.
Thank you so much. Yeah, thanks everyone for coming to my talk. It's such a great pleasure and privilege to be speaking about my joint work with Will here. As I'm sure everyone here has heard of, we have this notion of twin primes, which is a pair of prime numbers whose difference is exactly 2. And the conjecture that motivates some of this work is that there are infinitely many such twin primes. You don't have to restrict the difference to be equal to 2. In fact, you can make the difference any even number and make such a conjecture. This would also be sort of equally plausible. As an example of a very big pair of twin primes, I have this one, which I think is sort of the biggest example we know to this day. There has been many works and results towards this conjecture. For example, it was shown that there are infinitely many primes for which p plus 2 has at most 2 prime factors. This is, of course, a striking approximation to the result that we want to get, but it also sort of suggests part of the difficulty in the problem, that it's very hard to control the parity of the number of prime factors of p plus 2. So we know that p plus 2 has at most 2 prime factors, but we can't tell if it's 2 or 1. We can control the parity of the number of prime factors. More on that later. So another striking result in this direction, which made a very big breakthrough at the time, was a theorem of Etang Zhang, which showed that for some choice of h, which he couldn't quite determine, the conjecture has a positive answer. In fact, he showed that this h can be taken at most some big finite number. So there is some interval of fixed size where you will find 2 prime numbers. This was later improved by James Maynard very shortly after Zhang's work. So Maynard made this constant much smaller by a somewhat different method, and he also obtained very strong results about not only pairs of primes, but also triples, quadruples, and other tuples. So a lot of primes in very short intervals for infinitely many such intervals. This was further improved by the polymath projects, also very shortly afterwards, with some. So the state of the art today seems to be infinitely many primes for which p, for which there is a prime between p and p plus 246. So this is some of the works that have been done on this conjecture. Yeah, please feel free to stop me at any point with any questions or comments that you have. That would certainly be very welcome. So now I want to sort of shift gears and talk about something which is essentially very different from what I've talked about on the first slide. I want to view the problem of twin primes via the lens of the number field function field analogy. Or in more elementary terms, I want to replace the number system or the ring of usual integers by the ring of polynomials over a finite field. So it will be a completely different thing, but the analogy between the two, the similarity is quite striking. So we have, for example, the notion of prime numbers in the integers, which corresponds in this analogy to polynomials over a finite field which are irreducible, or monic irreducible if you want to fix the sign. And many of the things that are true over the integers can be proven in much the same way for polynomials over a finite field. For example, we have a unique factorization theorem, which works in both settings in a very, very similar way. When we represent integers using digits, for example, say in base 10, it's very similar to how you represent polynomials where the basis is the powers of the variable. There's also finitely many units in each of these rings. So these rings are very, very similar. And as I was saying, you can transfer results from the integers to polynomials for almost any result. But in some cases, you can say a little more about polynomials, and this is somehow part of the context of this lecture. So this is the result that the main result that I want to talk about today. It's the solution under some additional hypothesis of this twin prime problem in the setting of polynomials over a finite field. So the translation of the analogy should be sort of straightforward. So you expect infinitely many pairs of polynomials whose difference is a fixed polynomial. So it's supposed to be straightforward to make the translation. And again, the analog of prime numbers here are monic irreducible polynomials. Albeit we don't quite get this result, but there's an extra assumption that we need to make, unfortunately, at this point, although we're still working on removing this assumption at least partially. So the assumption makes a restriction on the size of the finite field over which we work. So you have to fix this. Once you fix the finite field, you're working in a certain world, in a certain ring of polynomials in one variable over that field, and you can think of the analogy to the integers for this particular polynomial ring. In that sense, this is a sensible analogy. So there has been also quite a bit of prior work for polynomials over a finite field for this problem. So indeed, the analogy is quite old and goes back at least to André Weil explicitly and implicitly also much earlier, I believe. But even for this problem, when the difference polynomial, which is the analog of 2 in the integer case, is constant, is just like a scalar, this has been done in some weaker sense earlier, but without counting, without the asymptotic count of the number of twin primes, which I will explain later. There has also been a resolution of the case where h is a monomial by adapting to the function field setting the work of James Maynard. So it's another testimony to the fact that you can adapt results from the integer setting to the setting of polynomials, sometimes even getting a stronger result in this direction, or a slightly stronger. And I would also like to briefly mention there has been a lot of work where you change the setting completely. You can also, instead of fixing the finite field and increasing the degree, as is very natural in the setting, you can also do something which is maybe at first sight seems not as natural, namely to fix the degree of the polynomials and to let the size of the finite field grow. In that case, you're not anymore working in the realm of a single ring. The ring always changes, but you can still ask about the infinitude of a certain set. You can still make very meaningful questions and theorems. So in this talk, I will not be speaking so much about that aspect, but I need to say that it's there, and there has been so much efforts in resolving this, the problem, or many other problems in this setting. Oh, that's a very good point. Yeah, in 3 and 4, there's almost no restriction on P and Q. Definitely, even if there is, it's much weaker than our restriction. Yes. Yeah. Yeah, I think 3 and 4 can be proven with no restriction on P. Yes. Yeah, and the methods are very, very different, and therefore there are no such restrictions. Yeah, so I want to explain in which sense these items 3 and 4 are just very slightly weaker than our result. I want to explain that our result is in fact quantitative. So what we prove is in some sense a twin prime number theorem. So we don't only show the existence of infinitely many twin primes in that setting, but in fact we count them. Okay, so the way we set up the count is using the degree, which is similar to the size of an integer, so but on a logarithmic scale. So we want to count irreducible monic polynomials such that both the polynomial and the shift of the polynomial by some fixed other polynomial are monic irreducible. And we obtain something which is in many ways the expected count. So there's some constant there which I'll explicate over here. So maybe I want to spend a little bit of time explaining what this asymptotic is. So as you may know, there's the prime number theorem, which is somehow the archetype of these kinds of results, which says that the number of primes up to x is something like x over log x, maybe with some error, which is very important, but we will neglect it for now. So when there's a similar result for polynomials over a finite field, but you just need to know what to replace x by. So x, the size of an integer, is analogous to q to the n if a polynomial has degree n. Because the size of an integer is the number of elements in the ring of integers when you mod out by this particular integer. And when you mod out by a polynomial of degree n over fq, the number of elements in the quotient is going to be q to the n. So a reasonable measure of the size of a polynomial is q to the power the degree of that polynomial. And indeed, the prime number theorem for polynomials over a finite field is the result that the number of polynomials that are monic irreducible of degree n is q to the n over n, which is very much like x over log x. So, and this is a more classical theorem that goes back to Gauss and says that the chance that a random polynomial is irreducible is also essentially 1 over log x, as much as the chance that a random number is prime is 1 over log x. And so you would expect, perhaps naively, that the chances that two independent numbers are both primes is 1 over log x squared. This is a very natural guess to make. But you have to somehow amend this guess, because if a certain number is prime, for example, then when you add 2 to it, it's already odd. So it feels that the chances that this another number is prime should be slightly higher than the chances of a random number to be prime, because a random number is even half the times. So to sort of take this into account, there is an extra constant here, what I denote by sigma q of h, that is supposed to take care of precisely that kind of subtlety. And I have written down this constant here explicitly. In fact, it was conjectured over the integers by Hardy and Littlewood. And you adapt it to polynomials over a finite field in a very straightforward way. But even if this constant looks a little complicated, what you basically need to know that you just multiply over the primes the probabilities that f and f plus h basically are both not divisible by that prime, which is basically what you need to do if you want to ensure that a certain number is prime. Sort of heuristically, you need to make sure that it's not divisible by the smaller prime numbers. So that's somehow where this infinite product, which at first sight may look a little scary, comes from. Moreover, you may want to know that this infinite product converges and that it's non-negative. It can be 0 precisely in cases which correspond to the situation you would have if you would try to show that there are infinitely many primes p for which p plus 1 is prime. That's of course false. There's a problem at the prime 2, and this infinite product will vanish because the factor at 2 will be 0. And there are similar things going on there for polynomials. So unless there is this little issue, this product is going to converge, be really positive. So this theorem, I want to emphasize, this theorem is not a vacuous result or says something contrary to what you believe. It will not show that the asymptotic is 0. It will really show that the asymptotic is some positive constant times q to the n over n squared. All right? Question? Yes? Absolutely, yes. Yes, the condition on P and Q, that nasty condition from the previous slide, exactly. It ensures that this sigma Q is non-zero. I think the only way in which sigma Q could be 0 is if P would actually be equal to 2. Yeah. Yes. Yeah, that's a good point. Thanks. Yeah, and so I would also want to mention that this theorem, much as the usual prime number theorem, it comes with a certain error term, but the error term in this case is pretty good as opposed to the usual prime number theorem. The error term that we are getting is a power-saving error term. So it means that if you take the difference between the count and the asymptotic, this difference in absolute value is bounded by the size that you expect, which is like q to the n, raised to a certain power which is smaller than 1. So it's in some sense a pretty strong bound on the error term. This bound gets a little weaker when you increase p, but it's still a power-saving error term. Okay, so I think this this is basically the introductory part where I've stated the result, and now I want to talk about the proof of this theorem, highlighting the similarities and differences between the function field and number field case. So the first key player in the proof is the Mobius function. I already alluded to the difficulty with the sieve methods in the previous results, where it's very hard to control the parity of the number of prime factors of p plus 2. And this is what the Mobius function does. The definition of the Mobius function is such that it precisely captures the parity of the number of prime factors. Of course, it also exists over the integers, but there is something special about this function for polynomials. But on this slide, I'll only say things that are true also over the integers, I believe. So the Mobius function is not sort of just abstractly important. It's also connected with the von Mangold function, or the indicator function of prime numbers, via a very simple combinatorial identity, which I just put on this slides. And this identity, with some technical difficulties, allows you to translate between questions about prime numbers and questions about the Mobius function. Yeah, for example, the prime number theorem and the Riemann hypothesis, they can also be stated as equivalent statements for the Mobius function instead of prime counting if you want. So here, what I want to do in the next 2 bullet points is to give you 2 statements that you need to prove if you want to prove the twin prime conjecture. So even over the integers, sort of the conjunction of these 2 statements is going to give you the solution to the twin prime problems. Unfortunately, of course, I don't know how to solve or approach any of these 2 problems over the integers, but I will explain the solution to some extent for polynomials. So the first problem is the Chowla conjecture, is the analog of the twin primes, but for the Mobius function. You want to know that, for example, Mobius of n is not correlated with Mobius of n plus 1. In other words, if you know that n has an even number of prime factors, it's essentially not going to give you any information about the parity of the number of prime factors of n plus 1. And this is very sensible because there doesn't seem to be any connection between the way that n factorizes and the way n plus 1 factorizes. seems reasonably independent events. So that's the Chowla conjecture. And the other one is the question of level of distribution for primes and arithmetic progressions, or a quantitative version of the classical theorem of Dirichlet. So the Dirichlet proved that, famously, that an arithmetic progression contains infinitely many primes, or a certain amount of primes up to x, if you demand that the difference of the progression is co-prime to the first element of the progression. But what I want here is some quantitative statement which will relate this number of primes up to x with the modulus of the progression. So I want to allow the modulus of the progression to grow with x. That's the kind of uniform statement that I want. In fact, I want the modulus of the progression to be of size at least square root x, maybe a little more, and still be able to find primes in this progression up to x. It's a very reasonable thing to demand on probabilistic grounds, just because the chances to be a prime number are so high, like 1 over log x. But this is, in fact, one of the central problems in analytic number theory of the integers up to this day, and it's very difficult, I believe. So, but in this talk, I will sort of address this for polynomials over a finite field. Yeah, question, yeah. Yeah. Well, yes, there is something to there is something to discuss here, but the way we do the proof in our paper, we can't remove this this part by some bounds on average or sieve theory methods or something like that. I think, if I may, I mean, so in James Minard's paper, I think he sort of sacrifices something. He doesn't work towards an asymptotic, he works towards just the infinitude of primes with a certain property, which allows him to also get away with like a slightly weaker assumption on the level of distribution. But because we work towards an actual asymptotic, we have to make slightly stronger assumptions. But I agree, if we just want infinitely many, that would be a little, it would be more likely we can weaken this assumption. So, yeah, so in the Chowla conjecture, that's the result that we obtain. So again, just to recall, this is for the first bullet, for this bullet point over here. In fact, we obtain such a result which works not only for correlations of 2 points, but correlations of any finite number of points, at least under the assumption that we can enlarge Q. So it's a pretty general solution of the Chowla conjecture in the function field setting. So in the language of the previous slide, it doesn't only say that the parity of the number of prime factors of n and n plus 1 are independent, but also of n, n plus 1, n plus 7, or any other kind of linear functions, number of linear functions in n, not just 2. You can also see here the decay of the power saving with p that I was mentioning in one of the previous slides. One kind of crucial attribute of this result is the uniformity that we have in the linear forms ai, bi. We can increase them with the degree of f and still obtain such saving. So this is, in particular, includes sums of Mobius and arithmetic progressions and problems like this. This is a technical point which is important in the argument, and the analytic number theorists in the audience may appreciate. Again, I'm mentioning that similar results were known in the large finite field limit, when you increase the size of the finite field, but keep the degree fixed, which is a different regime from the one I'm working on right now. And I would also like to mention one of the state-of-the-art results on such a question over the integers. So this problem of the Chowla conjecture has, of course, attracted enormous attention also over the ring of usual integers. And one of the results, the strongest results that we have in the literature, at least for general k-point correlations, is a theorem of Kaiso Motomaki, Maxim Radziwill, and Terry Tao, which essentially says that the Chowla conjecture holds if you allow an extra averaging over the shifts, if you allow some extra averaging over the linear form. So it's some slightly weaker result that is known over the integers, but it's still very useful for many kinds of problems. Okay, so I would like to now get into some of the more technical details, namely the proof of the Chowla conjecture. So I would like to explain how a statement of this sort in the first bullet point is proven. So far I mostly spoke about things which are common for integers and polynomials. The next slide sort of contains a twist or a change in the plot where I will speak about things which are very special for polynomials and do not seem to have any analog over the integers. So it starts, for example, in this problem with this identity for the Mobius function, which is very, very special for polynomials and is just not there for usual integers. It uses a whole host of extra structures that we have for polynomials. So for example, polynomials have derivatives, which is what you see at the end of this equation. Polynomials have discriminants and resultants, which we don't have for integers. Polynomials have Galois groups or actions of Frobenius on their roots, which is not something that we have for integers. All of that extra structure is somehow behind the scenes here in this equation. And it just comes basically from the fact that, well, the discriminant of the polynomial or its quadratic character is what controls the question of whether the Galois group of the polynomial or the action of Frobenius in this case is an even or an odd permutation. And of course you can check whether a permutation is even or odd just by knowing the number of cycles in this permutation, or the parity of the number of cycles, and the parity of the degree of the permutation, the number of elements it acts on. What I mumble about now is basically a proof of the first equality, and the second equality is just a general definition of the discriminant in terms of result. So it's some basic polynomial arithmetic that we're using here. And on top of that, which is a lot of extra structure in the polynomial ring, we're going to use even more structure that is very unique to the positive characteristic setting in which we are, which is the fact that in positive characteristic, many polynomials have the same derivative. In characteristic 0, two polynomials will only have the same derivative if they differ by a constant. But in positive characteristic, of course, they can differ by a polynomial in the variable to the power of the characteristic. So that observation allows us, when we try to prove the Chowla conjecture in the setting, to split the summation over polynomials that have a fixed derivative and then have another summation over which we sum trivially of all the possible derivatives. This is a very analytic step, but it's only possible for polynomials over a finite field as far as I can tell. And this trick is not particularly new to our work. It has already been used in different contexts by other mathematicians previously. So if you do this, so you fix the derivative and you run over all polynomials with a given derivative, what you end up getting after using some reasonably simple arithmetic like Chinese remainder theorem, some algebra around the Frobenius automorphism, which is reasonably elementary, you end up getting some very simple character sum. It takes a little bit of work to see how you really get it, but this technical step I will, for simplicity, I will skip. It's not very difficult to do. You essentially get a certain sum, which has also been studied in analytic number theory under the name of a short character sum. Yes, this is a short character sum. The character chi here is just the quadratic character, so you should essentially think of chi as the Legendre symbol. That's a quadratic character. So you need to get cancellation. That's eventually what things boil down to. You need to get cancellation in this short sum of Legendre symbols. There are also other sums that you get for various values of the derivative, which are more technical, but their treatment is not as novel. So I will leave this out because the methods that are used there are more standard sieve methods. So we have used quite a bit of machinery from positive characteristic arithmetic or arithmetic of polynomials, but now we are back again to a problem which also has a clear analog over the integers and has in fact been studied also in the classical setting of integers. So maybe to explain, this is also a very elementary problem. In fact, so imagine that G, this polynomial, maybe corresponds to some prime number, analogous to some prime number, and then you look at the range from 1 to p, and you're fixing some sub-interval, and you're asking whether in this interval the quadratic residues and non-residues are roughly equal in number. That's basically the question. It's a very simple sounding problem which on heuristic, on statistic grounds should have a positive answer, but it's still remarkably tricky because the intervals we are interested in are fairly short. That's roughly the kind of question. And there's a famous bound in the analytic literature due to Burgess, which is good enough as soon as the length of the interval is the total length from 1 to p raised to power 1/4. So the degree here would be allowed to go up to degree of g over 4. That's what it happens to be for polynomials. But unfortunately, the intervals we are interested in are quite a bit shorter, and an application of the Burgess bound will just not quite be good enough for our purposes. So what we ended up doing is improving this Burgess bound in the setting of polynomials. Of course, over the integers, this Burgess bound is still a sturdy kind of thing to improve. The problem still stands. But in the setting of polynomials, we were able to get somewhat better bounds for short character sums. So this is the statement that we were able to prove. This is quite general. I've stated it in the generality of an arbitrary Dirichlet character, which we do in the paper. But of course, as I'm emphasizing, the main case of interest for us is just the quadratic character. This case is maybe has a little bit of a more elementary feel, even though the difference between the two is not that big. Yeah, so this is, just to emphasize again, over the integers, the analog is summation over a short interval. What we have here is the function field analog of a short interval is all the polynomials whose difference has small degree. That's how the analogy works. And the estimate that we're having is something which at least looks like square root cancellation, which is what you would expect. You would expect that if you perform a random walk, when you walk to the right of the Legendre symbol is +1 and you walk to the left if it's -1, that it behaves like an honest random walk. And this result is the kind of statement in this direction that we are able to prove. Although this binomial coefficient which we have here will sometimes become non-negligible as compared to the square root cancellation term, and even this bound, when the interval becomes shorter and shorter, will eventually be worse than trivial. So it's an improvement of the Burgess bound in some cases, but in some cases it's still not solving the problem completely. But this is basically, I believe, as good as we could do using our geometric methods. So that's the bound that we got. So yeah, I want to basically explain next how algebraic geometry and the machinery, the abstract machinery developed there, can be used to approach such a question. And this is a fairly typical situation in this setting where we translate problems from integers to polynomials, and eventually we use the machinery developed by Groth and Dick and Deline to solve some problem in algebraic geometry that gives us a solution of the problem for polynomials. Yeah, so again, there was prior work on the large finite field limit. Yeah, so here is the way you do this. It's somehow I tried to sketch some reasonably elementary approach. It's not very hard to convince yourself that there is going to be an algebraic variety whose point count is going to control this character sum, at least if it's a quadratic character. Because you need to test whether this f plus h is a square or not modulo g. At least that's the situation if g is an irreducible polynomial, which is sort of representative of the general situation. And to test whether something is a quadratic residue or not, you can write a corresponding algebraic equation. So you take an auxiliary polynomial, you raise it to a square, you reduce modulo g, and you demand that this is equal to f plus h. These are all algebraic operations which are not hard to encode using equations over the finite field. So at the end of the day, many of these questions in analytic number theory over function fields, they boil down to problems of counting points on algebraic varieties. Maybe the more kind of highbrow approach to this would be to speak about trace functions of sheaves instead of just point counting on algebraic varieties, which would make this a little more transparent how this works without having to write complicated equations. Later this week, we'll have a wonderful talk by Philippe Michel, who will explain the theory of trace functions and its multitude of applications, not just over function fields, but also over the integers. And so I'm leaving out this part completely. And of course, the key to being able to solve any of these problems is the Groth and Lefschetz trace formula, which allows us to translate problems about counting points on an algebraic variety to questions of estimating the cohomology of this algebraic variety when you base change it to the algebraic closure of the finite field you work with. And so the kind of cohomology we work with here is étale cohomology, but it's in its properties and the way it works is strikingly similar to singular cohomology, to many of the other cohomology theories we know. And so the study of the traces of Frobenius on that cohomology, or just the cohomology itself, is very similar to problems we usually handle in topology, maybe, or in complex algebraic geometry, for that matter. So working here over an algebraically closed field makes the situation very much like working over the complex numbers. And so the key to being able to do that is an understanding of the geometry of this variety that we have defined by equations. And in this case, the geometry ends up being very simple. The variety ends up being a complete intersection in projective space. But moreover, it's almost a smooth complete intersection. Did I write this here? Yes. Uh, it ends up having isolated singularities, which is almost as good as being non-singular. And because of the simple nature of the variety, that it is a complete intersection with isolated singularities, maybe the case you should think as an example is maybe like a smooth hypersurface. The geometry of such a variety is very similar to the geometry of a smooth hypersurface. And for smooth hypersurfaces, we can get very strong information on the cohomology. So the cohomology of, for example, of a smooth hypersurface in projective space, let's say over the complex numbers, is very similar in most degrees to the cohomology of just projective space of the same dimension. And that's exactly the situation that we have here. The cohomology agrees with that of projective space up to some very small set of degrees, 2 degrees of cohomology, where the cohomology could be potentially different. And the way usually that one studies the cohomology, for example, of smooth projective hypersurfaces, or at least one way to do this even over the complex numbers, is to put this hypersurface in the family of all smooth projective hypersurfaces, say of a given degree. And then as you vary over the family, because for some of these hypersurfaces in the family, it's easier to compute cohomology than for others. You can do it for those, and then you can show by a method of vanishing cycles, for example, at least in the algebraic setting, that all these hypersurfaces have essentially the same cohomology. So you vary over the family, and you learn that all of them have the same cohomology, and you can compare to a specific member of the family, and from that infer the kind of information that you want about the particular member that you are interested in. And what we do here is very similar even for those cohomology groups which we can't control just using the non-singularity. We perform such a vanishing cycles argument, such a comparison of cohomology argument between the short interval corresponding to f, so that the short interval we are interested in, and the short interval that corresponds to f equals 0. For which the bounds on cohomology and everything we're interested in will just be a consequence of the Riemann hypothesis. And this is something also very, very unique to the geometric situation. In usual analytic number theory, there doesn't seem to be a way to compare short character sums for different intervals. And even if there was, you would need to use the Riemann hypothesis to get somewhere. So definitely one of the key inputs into our result is Deligne's Riemann hypothesis, which is a very powerful and very general Riemann hypothesis proven by him in the setting of function fields. In this case, it manifests itself in bounds on the eigenvalues of Frobenius on the cohomology. So some cohomology groups we can't quite control, like these two cohomology groups which are not like in projective space. And for those, we use the bounds of trace of Frobenius on cohomology. We bound the trace by just the sum of the eigenvalues, for which Deligne gives us a very strong bound. And that's precisely where the error term in our bound, the shape of the bound, where it comes from. It comes from the bound that Deligne gives us on the eigenvalues and the dimension of the non-vanishing cohomology groups. All right? So that's basically the strategy to prove the Chaulat conjecture. Oh, the Betti numbers, so they are in the middle. So it's the Betti numbers that, so if the dimension of the variety, so you see, so the Betti numbers a priori, they go from 0 up to twice the dimension, as you see in the formula, and the non-vanishing ones, or the potentially non-vanishing ones, are the ones that are in the middle. So in degree I equals the dimension of the variety, and then in the degree I equals the dimension of the variety plus 1. These are the two Betti numbers that we don't know that they vanish. And it's very convenient for us that they are those that are in the middle, because it's precisely for those in the middle that Deline's bound gives you the strongest possible estimate on the eigenvalues. If they were somewhere closer to the top, we would not be able to obtain the result using that kind of argument. Yeah, we would need to know something about what the eigenvalues actually are. Whereas here we can employ a much cruder strategy where we just need Deline's bound on the size of the eigenvalues. Okay. Yeah, and so this was basically for the first problem that we need, which is the estimation of character sums. Yeah, question. Yeah, Philippe. Yeah, definitely. No, even if there wasn't the plus one here. Yes, exactly. Yes, but I have to say, I think that even if there wasn't the q to the 1/2, it would still be a similar problem. I feel like one of the significant sources of the problems here is this binomial coefficient. And it is precisely this estimate, as you're saying, that is responsible for the undesirable assumptions in our theorem, such as q is bigger than something depending on p, and so on and so forth. And in fact, in all results in analytic number theory over function fields proven via this strategy or something similar, there will always be, at least all examples I've seen, some Betti bound, and as a result, there will always be some assumptions on q bigger than something. It's also curious that recently there has been some paper by Will where there has been an assumption that q is bigger than something which comes from a different kind of source. But this is, yeah, so this is something very typical. Yeah, it's something I thought. Yeah, it's a very good question. Something I thought about. Unfortunately, I don't know how to do that, but we do have some kind of slightly different approach to the problem, which would allow us to get rid of some of these assumptions. So in this other approach we're thinking about, we would still need to assume that q is large enough. So let me maybe just go back to the assumption so that we see what we're talking about. Yeah, so the bound was over here. Yeah, so it's this assumption that we're trying to remove, the assumption in red. And the worst part for me about this assumption is that there is a dependence between q and p. That's somehow the worst part. We want to improve this by demanding instead that q is large enough. This could in some cases be worse than this assumption, but at least there won't be a dependence between q and p, besides q being a power of p. And that we hope to do by some slightly different method. Although some other avenue of research which seems kind of curious to me is like how to get rid of this p greater than 2, p bigger than 2 assumption, which doesn't seem to be there for for many of the other theorems in analytic number theory over function fields. But for example, in this approach, you see why I'm assuming that p is bigger than 2, because in this formula that I was writing here, yeah, I'm using the existence of a quadratic character, which just wouldn't be there if you don't assume that p is bigger than 2. And in the other approaches we also use something like this. Even though there is an analog of this formula in characteristic 2 due to Berle count, I don't quite know how to use it to prove an analog of the result in characteristic 2. yeah, so the other problem I was going to talk about, right, is after we talked about the Chowla conjecture, is the question of the level of distribution for prime polynomials or for the analog of prime numbers in function fields. So this level of distribution is how large you can take the modulus as a function of the size of the integer. So again, just to recall what the problem was, as in Dirichlet's theorem, we take two things which are co-prime, and we want to count the number of primes in this progression, but they have to be smaller than roughly the modulus squared, or something like this, yeah. Or maybe even smaller than that. So that's what we managed to do for polynomials over a finite field. Again, quite a few works on that in the large finite field limit, which I'm mostly skipping. And in this case, we are also basically employing a reduction, which is also valid, I think, in the case of integers, just the reduction itself, not the solution to the pieces in the reduction. So we break the problem of the level of distribution into two problems. One of them is the problem of the level of distribution for Mobius in arithmetic progressions. So what you want to know is if you vary over some arithmetic progression with uniformity, that the number of the progressions in this progression are equally likely to have an even versus odd number of prime factors. This is, again, a very viable conjecture to make on statistical grounds, but it's very difficult to prove. In the second part of the problem, which has in fact already been resolved over the integers by Etienne and Philippe, who is here with us, that you want to sum the Mobius function against the value of an additive character on the inverse of the polynomial to some modulus. So I'm writing the summation here modulo m, but I really mean the summation over the representatives given by polynomials of degree less than m, or if you do over the integers, by integers less than m. It's a very specific kind of sum. And using the methods of trace functions and other ideas such as Vaughan's identity, for example, I believe, or Hid-Brown's identity, you can use one of those identities. This is treated in the work of Etienne and Philippe. And in Philippe's talk, I believe, at least for the analogs of these kinds of sums over the integers, you will have an explanation of how to approach that kind of stuff, which also involves algebraic geometry and the Grothendieck-Lefschetz trace formula. And the question of sums of Mobius and arithmetic progressions in our work for polynomials is treated in a similar way and is in fact already part of the Chowla conjecture with uniformity in the case k equals 1. So yeah, I think that's basically all I have prepared for today. I would like to sincerely thank you for your attention and questions. Thank you so much.
Are there any questions?
Could you talk about, again, like exactly where the problem arises between the gap between P and Q? Like which lemma is problematic?
Or? Oh yeah, I mean the whole approach. Yeah, so there is this our paper in this case. It employs in some sense an approach which is a little convoluted. And this is the case where we split the summation into polynomials having the same derivative. So when we go back somewhere here, yeah. Yeah, so it's this step where we take a certain summation and we sum trivially over the derivatives and then try to get cancellation in the sum over polynomials which have a given derivative. This is a very unnatural step. Of course, it's also not analogous to anything over the integers. And once this step is performed, I don't think that current methods are able to obtain a dependence on Q in Q which doesn't involve P. Although some of the ideas that Philippe suggested, if it was possible, if it was somehow possible to get a bound here which is a little stronger, which is maybe possible but not by methods of the growth and Nikolai-Evshets trace formula or something we do in this paper, if you could improve somehow this bound, which seems very difficult but still may be possible, you could maybe get rid of this undesirable dependence between Q and P.
So the dependence is through like the degree of G here somehow?
So yes, not quite. The degree of G is going to be arbitrarily large when we apply this result. But it's roughly the exponential growth rate that is problematic. So the degree. So the point is that the degree of G, you should think about it as like a multiple of T basically. So you're computing some binomial coefficient, which is like n over some small multiple of n or something like that. And this grows exponentially, and that's where the problem basically comes from.
Okay, thanks.
Yeah, there is a question over there.
So we have a result about twin primes in over the function field of a finite field over T. And as we know, the global fields also include finite extensions of this field. So do you think similar methods to this one generalizes to finite extensions of a function field?
Yeah, I strongly suspect this is possible. Yeah, I haven't worked out details. And unfortunately, many of the results we have over function fields are not extended to function fields for curves of higher genus, as you were suggesting. But in that setting is somewhat less convenient to work with. Maybe that's the excuse I can use for why people didn't do it, in that various rings of integers there are not quite unique factorization domains. So there's some distinction between, irreducible or prime elements on the one hand and prime ideals on the other, which doesn't quite arise when you work over Z or just polynomials over a finite field. So that makes the question a little different, but it's still possible to try and extend the results to that setting.
All right, yes. And another question. So on the last slide,
yes.
What is the meaning of that number a half plus 1 over 100?
Yeah, good question. I was somehow used different kinds of notations. So in the notation I'm using here, basically what you want to do is if you're counting primes up to x, then you want to use a progression where you allow the modulus to be x to the 1/2 plus 1 over 126.
So in the first statement, the m is about square root of the length of the counted interval.
Yeah, right. But you want to be a little over the square root.
So we want a larger modulus.
What?
So we want m to. So we want to use a larger modulus.
Exactly, but just like a tiny bit larger.
Yeah.
Anything larger than 1/2, anything like properly larger than 1/2 would work. Yes. But the 126 is just an artifact of the methods and the approaches that we were using in that particular paper. But it doesn't have any kind of very high significance beyond that. Yeah.
Thank you.
Okay, thank you.
If there's no question, let's thank the speaker again.
Thank you so much.